Oh. It's even worse. Now there's no chalk whatsoever. Not only the bad ones.
There is some.
Huh?
There is some.
Very little. Especially if it is the bad one, because it crumbles in a... Can we get some extra chalk?
Yes.
Yeah, maybe from buckets.
Huh? Yeah.
You can steal it from the previous.
Yeah.
We are recording.
I think that's a normal thing to do.
Sure, of course. What else can you do? Just transfer. It's called transfer. Okay. So we wait a little bit, but just to tell you, yeah, these are the bad ones. We want to do today one-dimensional problems, Schrodinger equation problems, okay? Better, time-independent Schrodinger equation problem, okay? So let's wait. Fantastic, these are the good
Yeah,
ones.
tiny pieces.
That's okay, but these are usually big. Okay, can we do it the rest?
I
Later.
don't know.
Okay. Well, let's skip it. Okay. So, the problem is the following. I have a Hamiltonian operator, and I want to find, generally speaking, in more than one dimension, this is a vector, so wave function, function of x, En, the eigenvalue, Pn of x, okay? If you remember, H for non-relativistic problems, one part of the problems we are dealing with is simply equal to p squared, the momentum operator squared, divided by twice the mass, plus the potential. Okay. Now, let me start. So this is the problem. Let me start with some general consideration, which apply also to higher dimensions. So suppose I have some potential, which has some minimum, okay, whatever, okay, some potential, V of say x. I mean, I have difficulty drawing, but suppose that x depends only on the distance from the origin, then I can draw this, okay, and there is some minimum, V min, okay. Then the first thing that I would like to discuss with you is that don't look for any eigenvalue below this minimum, okay? So this should be the first thing that should be clear to your mind. So the spectrum cannot be below the minimum of the potential. Obviously, there are potentials which do not have a minimum. For instance, the Coulomb potential doesn't have a minimum. And at that point, this wouldn't tell you much. But there are potentials where there is a minimum, and there this bound applies. Let's see why. Okay, the proof is very, very simple. Let's take this eigenvalue problem, and let's take the scalar product of the eigenvalue problem with phi n itself. Okay? So here I have h phi n. Remember, I can add the bar, but it's up to you. The Dirac notation or... Okay, and here I have En phi n phi n, right? Now, assume that the wave function is normalized, so this is 1. Okay, so this is En. Fantastic. Now, what about this? This is sum of two terms. The first term is phi n p squared over 2m phi n. This is the kinetic energy contribution plus phi n v of x phi n, right? Let us start looking at the first one. It is a bit deceptive if you write it in terms of the Laplacian, okay? Because it looks like there is a minus sign. But I told you, danger. Don't look at minus sign and deduce false things. This is, in fact, I can show you, non-negative. Why? Because you can also rewrite it as 1 over 2m. Remember, this is p squared and p is Hermitian, okay? So you can bring p to the left, so p phi n, scalar product, obviously, okay? So sum of the, and now you see immediately that this is the scalar product of a function with itself, so it's the modulus square, this is the modulus square of this object here. And in fact, you can rewrite it as h bar square over 2m, the integral in dx, the gradient of the function phi n modulus square. Okay? So you see this is positive and tells you how much the wave function varies. Okay? The more it varies, the bigger is the kinetic energy. Okay? The more it's flat, the less you pay kinetic energy. Okay? Is it clear? Now, it is based on the positivity of the square of the momentum, which in fact is true for any Hermitian operator. If you square an Hermitian operator by the same argument, the expectation value of, well, we'll discuss more about expectation value. The brackets say within the same state, it's always positive. Okay, so it's a very general thing. If I have an Hermitian operator and I square it and I calculate this, whatever state you take, it's always non-negative. Say, okay? Fantastic. So the kinetic energy is non-negative. And what about the second contribution? Let's write it. Is the integral in dx. Then I have Vx times phi star phi, okay? Which is phi n of x modulus squared, okay? This is, remember, the probability for finding the particle at position x in the state n. Right? A positive quantity. Now, and this is the potential. Now, this is a kind of the average value of the potential weighted with a probability distribution for positions. Okay? Now, if the probability was all sitting in this point, perfect delta function, I would obtain for that integral the value v min. But since the probability in general is spread, okay, and is not just concentrated in the minimum, then you are sensing parts of the potential which are above the minimum, okay? So in general, you expect that this is not less than the minimum, okay? In fact, the limiting case of a delta function probability gives you exactly the equal sign, okay? So, not, say, in general, greater or equal to 0 this, and greater or equal to v min, the other term, the result is that the sum of these two terms is greater or equal to v min. But this, if you follow the thing, is just En, okay? So, I have proven this, okay? Very general. Now, a few considerations about the spectrum. I told you the spectrum is the set of all possible eigenvalues. There are an infinite number of them. They cannot be below the minimum of the potential. What could happen? Several things. For instance, let me just draw an example potential like this. Okay? Something like this. Okay. Like this, for instance. Okay? So there is a potential that somehow here approaches 0. Okay, in this way. and here approaches this, another value. So what happens? Well, there is a minimum. Okay, so the eigenvalues cannot be below here. There are usually, there is certainly one bound state, but maybe more than one, which means a discrete value of, so say, E1, E2, discrete. Okay? The discrete part of the spectrum is in between the minimum, okay, and the value of the potential at infinity. Okay? These are associated to wave functions that are somehow bound. They're called bound states. Bound states. Which means that their probability is just essentially different from zero in a finite region of space close to this region. Okay? And they are normalizable. Normalizable. Okay. If E is larger than this, okay, you can still have eigenvalues, but essentially the wave functions behave as plane waves far away, okay? Then they are modified by the potential, obviously. They are not exact, but you can find for any energy a solution, okay? So this part is a part of continuous spectrum, okay? Remember that the free particle has exactly a continuous spectrum, right? Now we are learning that there could be also parts with discrete spectrum associated to normalizable functions. So these are usually actually non-normalizable size. Okay? And you could ask what is the difference between, say, this part. So suppose that this goes here and this goes to this position. Now, there is this part of the spectrum in which essentially you can find only waves that come from here and then return back. We'll see scattering problems later on. So there is only one solution here, while in this part here you can even find two degenerate solutions, okay? One that comes from here and one that comes from there. We'll discuss this later on in when we will study the scattering by step. Okay? So wait a little bit more. Okay. So this is the general thing about bound versus continuous, non-normalizable wave function, discrete spectrum versus continuous. In the hydrogen case, for instance, we will find a situation like this. The potential is no minimum. We find an infinite number of bound states, okay? And then a continuous spectrum where the electron is essentially approaching a proton, but like a comet is going away. The harmonic oscillator, okay, on the contrary, is a case where the potential never approaches zero. It increases without bounds. Okay? In this case, the spectrum is fully discrete. Okay? So there could be all possible situations. Purely continuous spectrum, purely discrete spectrum, both, okay? And even an infinite number of bound states and a continuous part of the spectrum. Okay? So be ready for all possible situations. All right. Now, let's finally discuss one final general aspect of the story before we dive into simple problems that we can solve. Okay. When we look for solutions of problems, obviously we want wave functions which are continuous. Okay? Physically, obviously, mathematically, the mathematicians show that the solutions of these problems are continuous and differentiable, blah, blah, blah. But physically, the continuity is associated to the fact that the probability of finding the particle somewhere is the modulus square of x, okay? This probability cannot have jumps at point, I mean, for physical reasons, somehow. Well, but you could ask, what about the derivative? Let me write it as phi prime. In 1D, this would be just the derivative of phi n, okay, just for shortness. Is this continuous or not? Well, generally speaking, yes. After all, here I have the second derivative. So I want to have something for which I can take two derivatives, right? And therefore, the first derivative is generally continuous, and you can take a derivative, in fact. Now, let me show that you expect, indeed, that the first derivative is continuous, even at points where the potential might have a jump. It could happen that you have a potential that does something like this. Obviously, you might say, but this is a mathematical, very singular thing. Yes, obviously, is the mathematical idealization of something which occurs somehow in a very, very short distance, which you want to ignore somehow. But let's assume that you have a really discontinuous potential. Okay, so the potential V of x has some discontinuity around some position x0. Now, I want to argue with you that nevertheless, the wave function derivative, not only the wave function, but even the derivative is continuous there. Let's see why. The argument is not difficult. It is essentially the following. Let's write the Schrodinger equation. The Schrodinger equation looks like this. Minus h bar squared over 2m. The second derivative. Okay, let me write it in this way with respect to x. Plus v of x, phi n of x, equal to en phi n of x. Okay? Now, let me do one thing. I bring this on this side, and I write it like this. En minus vx phi n of x. Okay? Here, I just brought potential part on the right. Now, I do the following trick. I integrate this object between x0 minus epsilon and x0 plus epsilon, where epsilon is a small quantity. So you decide here a small interval. This is x0 minus epsilon, and this is x0 plus epsilon. Okay? I want to understand somehow what the derivative of this function does at this point. Will it do something like this with a cusp, or will it do something smooth with the derivative equal on two sides? Okay, this is my question. I would like to understand if it is this that I should expect, or rather a cusp-like function. Okay? Now, can you do this integral on the left-hand side? Is the integral of the second derivative, right? Well, the primitive function is the first derivative, okay? So this is minus h bar squared over 2m. The first derivative calculated at x0 plus epsilon minus the first derivative calculated at x0 minus epsilon. Obviously, I have to integrate here as well from x0 minus epsilon to x0 plus epsilon. Okay? So this is equal, according to the equality above, to this integral. En minus v of x times phi n of x. Now let's look at the integral on the right hand side. This is a constant. This is something which is a function which possibly has a jump, but it doesn't diverge, nothing. It has at most a discontinuous behavior. And this is a function that is continuous. Okay? So the object is not continuous, but certainly is integrable. You can, for instance, split the integral in two parts. This first part and then the second part is totally integrable. Nothing really bizarre occurs. And you are integrating this integrable function in an interval that is 2 epsilon wide. Okay? Now, take the limit epsilon going to 0 of the left-hand side and of the right-hand side. What would you conclude from the fact that this is an integral of a function over a small interval epsilon, 2 epsilon, which when you take epsilon equal to 0, what do you think this limit will be? 0, okay? Because any integrable function, if I integrate on a vanishingly small integral, okay, because it gives me 0, okay? So, in some sense, this is telling you that the limit of the derivative from the right minus the derivative from the left is 0, okay? So I am in a situation where the derivative is not discontinuous, but rather smooth. Is it clear? Okay? So phi prime of x0 is well defined. Okay? Although the potential has a step. You see immediately that the argument or the proof fails if the step is infinite. Okay? So if I have a potential that has an infinite discontinuity, so here is infinite, say, and here is 0, then this object is not small. And therefore, you should be aware that phi prime might be discontinuous if there is an infinite jump. Okay? That's it. Clear so far? Okay, good. So let's start with our first problem. Okay, which is now a one-dimensional problem. So let me just, okay, and the potential is
For if the potential v of x is like a Heaviside step function,
yeah.
do we assume that like theta of x when x is 0 is 1/2, or
It's not important. When you calculate integrals,
still
0 measure points doesn't really matter. Integrals are very simple to deal things. So little difference in the function at one point make no difference for the integral. Okay? They are related to questions about continuity and things of functions, but when you integrate, it doesn't matter. Okay? All right. Now, so the potential that I want to deal with is, in fact, now a singular one. Okay? So exactly a case that I was telling you, be aware that if, okay, so we do the infinite square well, I will denote like this, so the potential is like this, this is x, this is the v of x. Now the infinite square well potential is infinite here, then it is 0 here, then it is infinite again, okay? I cannot draw infinities, okay? But here there is essentially an infinite potential, and here is 0, okay? In a region that is, let's see what notation I use, 0, L. Notice I'm putting the origin at the border of the well. Later on, we'll put the origin in the middle for a reason, okay, which I will explain later on. For the time being, it's quite useful to put the problem like this. So, it's a bit like the box of length L that we studied yesterday. Remember the periodic boundary condition, but now the conditions are not periodic boundary condition, because the wave function here should be 0. There could be no particle in a place where the potential is infinite. Okay? So here, in fact, phi n is equal to 0. Here, phi n is equal to 0. And therefore, by continuity, the potential is, the wave function is 0 here and 0 here. So the boundary condition, which I have to use now, are phi n of 0 equal to phi n of L equal to 0, however, not just equal. So they are equal and 0 and vanishing. Is it clear? Okay? Due to that argument, be aware that the wave functions will not be with a smooth derivative. Here the derivative is 0 from the left. And here you will see it's finite. Okay? So the derivative is discontinuous at the point. Okay? So not well defined, so not discontinuous in this case. Okay? Okay. Now, what about solving the problem here? So this is in 1D. Okay? So this is essentially, in this region, is a free particle. Okay? You remember what are the eigenfunctions of the free particle? Okay, with 0 potential?
Sine.
Just?
Sine.
Sine, cosine, or plane waves. Okay,
Yeah.
let's write them as plane waves. So you would have, say, e to the ikx, but also, if k is positive, also e to the minus ikx would be a possible solution. Okay, or you could think, okay, let me just make a combination, sine and cosine. Let's look at the sine, for instance. Okay? So this is certainly a solution. Well, in principle, for any k, you have a solution of the free particle problem there, right? What would be the energy associated with this? What is the energy? So I'm looking for now solution labeled by this k. What is the energy? Is e to the ik or e to that, so it is equal to, don't be afraid, it's the usual free particle thing, okay? Whatever k, there is the eigenvalue. So, conclusion, is this a continuous spectrum?
No.
Not really, no, not really, because I want to satisfy this, okay? So, now, why did I choose the sine? I chose the sine rather than the cosine because certainly in 0 is always 0, okay? So fantastic. So I write somehow the constant here, and this is phi k of x, and automatically in 0 is fine. But what about the value of the function at L? Okay, so the phi k L. This should also be 0. Now, it is not 0 for any L. Obviously, I have to impose, so this commands that k times L is what? When the sign is 0? A multiple? Pi. Fantastic. Good. Now, n should be what?
Any integer.
Is 0 okay? Let's discuss this first. Suppose that n is 0. If n is 0, k is 0. If k is 0, I have the sign of 0, which is 0. So the wave function is 0. Is this okay? Do you like wave functions that are 0 everywhere?
Because you can normalize that.
I mean,
no particle.
No particle. Okay? So the wave function should not be 0 everywhere. Okay? Otherwise, it's not a wave function. So actually, n cannot be 0. Let's see. Suppose that I take n equal 1. That's okay. But what about minus 1? Okay? So n equal to minus 1. Minus an integer in general. What happens? If you change sign, the sign changes sign. So the wave function, okay, becomes minus a, the sign of kx. Okay? If you send k into minus k. Okay? Well, but the wave function that is minus itself, is this really a different function?
But it's a phase.
Huh? It's a phase, it's in fact a sign, okay? So it doesn't really matter for the wave function because, I mean, for the probability is a modulus square. You might say, but the phase might be important. There are cases where phases can bring to interference phenomena, so you should not always be so careless with phase factors. But in this case, I'm looking for functions that are eigenfunctions, and obviously the factor that I put in front should be such that the function is normalizable, but I could even multiply it by I. It doesn't matter, okay? So the factor in front should be such that somehow the modulus square of this function, so the requirement, in other words, is that the integral of a modulus square, the sign of kx calculated between 0 and L, should be 1, right? A modulus square, doesn't matter if there is a binary, if there is an I, if there is anything you want. And in fact, if you calculate the corresponding coefficient, I think is square root of 2L. Yes, is this right? This integral is very simple. It's
Sine squared.
Sine squared kx.
sorry, sine square. Good. And the integral of sine square in the half the integral is 1 over 2L. So I think that this is a. The function here is square root of 2 over L, but check it yourself, okay? I didn't note on the lecture notes, okay? So it's an integral that is very simple, and I think that A is this. Okay, good. So, minus n is not a different wave function. So, what I should really take is n equal to 1, 2, up to infinity, okay? And the energies are simply h bar square over 2m. So k, we decided is n pi square m square divided by L square. Okay? So these are the energy eigenvalues for n equal 1, 2, and so forth. So let's see the smallest one. The smallest one, E1, okay, is equal to h bar square pi square divided by 2m L square. Okay? Then what about the next one? E2 is 4 times as big. So if this is 1, 2, 3, and 4. Here. Okay? E2 equal to 4 times E1. Okay? What about the next one? E3 is 9 times as big. Well, I don't do it carefully. E3 is equal to 9 times E1. And so on and so forth, up to infinite. So there are an infinite number of bound state, discrete energy eigenvalues. Okay? The difference between these things is governed by L. So if you increase L, they shrink. Okay? Now, you might think that this is, well, just mathematical divertissement, but people in solid state have learned how to make structures that are so-called quantum wells, heterostructure of different semiconductors, and with lengths that are, I mean, really very, very small, okay, of the order of a few nanometers, or, okay, 10 nanometers or so. So this quantization phenomena associated to small difference are important in practice when you create those structures, okay? So just be aware that with this seemingly artificial object, people have done wonderful things in semiconductor physics. Okay, what else should I tell you? What about the wave function? Okay, let's write the first wave function. So phi1 of x, the ground state, this is again A, which is some square root of 2 over L, times the sine of k, the lowest one, is what is pi over L times x. Okay? So you see, it is 0 here, 0 here. Let's draw it in the middle. Maybe I draw it like this. Okay? It's just this. Okay? It's this half of a full sine. Okay? It goes to 0 here and here, and it goes. Okay? Is it clear? What about the next one? Phi 2 of x is a sine of 2 pi over Lx. So let's draw it. It is this. Well, perhaps it's okay. It has a 0 here and a 0 there, an extra 0 in the middle. Okay? It does one full oscillation between 0 and that. And so on and so forth. You can go on 3 oscillations, 4 oscillations, and more as the wave vector appearing here increases. Is it clear? Try to draw them, a few of them. Okay? So you see, the more they oscillate, the more the energy increases. Why? Kinetic energy. Remember, the kinetic energy is sensitive to the integral of the gradient square of the wave function. Okay? So the more you oscillate, the more you pay in kinetic energy. In fact, there is only kinetic energy. You realize the potential energy is always 0. So it's a purely kinetic quantization phenomenon. Okay? Clear? Now, what else should I discuss?
It's really
Yeah.
more of a really stupid question, but it's strange that only allowed integers for n are positive, non-zero, but it seems that the boundary conditions is also satisfied when n is negative integers, but somehow we just said that
No, wait. I don't want to do this. No.
and the dispersion and the energy is squared
Is the square. So you might say negative n is the same.
still satisfies.
Yes. But the question is this one state only or 2?
Yeah, is it degenerate or not? Yeah.
So it is an important question. I mean, if there were 2 states, then this would be just too close by level, too infinitely degenerate levels. The answer is, I don't just ignore them.
Yeah,
It's the same state. In other words, if I write this state and I write phi1 tilde equal to
minus.
a sine of minus pi over Lx, this is equal to minus phi1 of x. Okay? Now, minus the state
Yeah,
would be
I understand that
this object. It's not a different wave function, okay? Because I can always, when I write a equal to this, I can tell you a equal to this times e to the I
Yes,
alpha.
of course.
Any phase is okay. So the minus is as well, okay? Right? So it's not that I want to get rid of this annoying thing. It is only one state, okay? This is important. Is it clear?
I mean, it was clear from the beginning, but still it's somehow...
You digest it and then after a while you say, the face in front is not important? Okay. Now, don't take this statement, the face in front is not important as a general fact. We'll see situations where faces are important. But here, a global face in front of a state is not important. Okay? This is a statement. So, if I change n into minus n and I notice that I just changed the sign in front of the wave function, this is not a different state, it's the same.
For example, in terms of interference, if we have 2 states, for example, phi of n equals 1 and phi of n equals 2, and we calculate the interference, we'll get some factor of plus. But if we take the state of phi minus 1 and phi plus 2, then the interference sign will be different. It will be minus.
I understand your thing. When you do calculation of that type, you should first write your wave functions, decide the convention on the phase, and at that point you can calculate whatever interference term you need. Now, this doesn't mean that this state is doubly degenerate. I know that the factors that you calculate in whatever matrix element you need depends on the choice that you make of these things. All right, be consistent, okay? But do not conclude that there are two states here. In fact, otherwise I would tell you not two, four. Put I or minus I, or in fact an infinite number of them. Put e to the I 2 pi over 3.
So,
okay?
The thing is that
this is the crucial thing, is that there is only one state. You have to decide what factor you put, what phase you put, plus, minus 1, I, whatever you want, and then when you do all your calculations, given the initial choice, you are consistent. And at that point you are guaranteed to get the right result. But don't think that because I can choose whatever phase, then I can change a physical result about the calculation, okay? No, this doesn't happen. Okay. All right. There are a few other things that I would like to discuss with you. For instance, what are, if I ask you, the following question, what is the average value of the momentum for these wave functions? Okay? What do you think? Huh? No, you can calculate. And the surprising result is 0. Okay? Let's see why. Okay? First of all, it's the average value of an emission operator. Okay? Now, I can prove in general that if I have a state and an emission operator, then this object is real. Is it clear? Why? Let's calculate the star. So the star of this is equal to, remember that the scalar products are, when you take the star, you have to invert. Okay? But this is emission, so you can bring it here. So this is also equal to psi A psi. Okay? A is equal to A psi. Okay? So you see that the star is equal to itself. So the object is real, always. So let's write, this is emission, is exactly the same thing. So this should be real. On the other hand, if you write it, this is equal to minus I h bar, the integral from whatever, 0 to L in dx of, say, A star sine of kx, okay? Then I take the derivative, okay, of whatever, A sine of kx, okay? So this is just modulo squared. Fantastic. Now, why is this 0? Well, it is 0 because, first of all, it must be real, and this is certainly real, and here there is an I. So better this is 0. Otherwise, something is wrong in our argument. Okay? And in fact, it is 0 if you actually look at the exact form of this thing, because this is a sine, and the derivative of a sine is a cosine. So if you just do a little bit of trigonometry, you realize that this is an oscillating function whose integral is in fact 0. Okay? But the more profound argument is that somehow, whatever is the function here, okay, if this is a real function, okay, somehow I have a real function up to a possible phase, phi, the derivative, okay, if the wave function is real, should be just real, and therefore here I have an I. So this object, when the function is real, is always 0. A real function cannot carry any momentum. And in fact, you notice that the sine of kx is just the sum of e to the I kx minus e to the minus ikx, okay? And you see that there are both momentum k and momentum minus k entering divided by 2i. Now, don't think that it's because of this minus. The cosine would also carry no current. So even if I have a plus and the factor 2 there, I still have 0 current because there is momentum plus k and momentum minus k with equal amplitude, okay? So the momentum is always 0 for any real function, and in particular for all these bound states. But p squared, okay, is not 0. And in fact, I told you that p squared is necessarily greater than 0 because it tells you it is essentially equal to p phi n p phi k. Okay? So this is in fact greater than 0. It is the modulo square of the gradient of these functions. Okay? And in fact, how much it is? Well, it's equal to the 2m times the energy eigenvalue. Okay? So the numbers that I've written here times 2m are the value of the p squared. So if I tell you what is the spread, okay, I can ask you several questions. For instance, I can ask you what is the spread of momentum in this function. Okay? Let's start with the spread square. As you know, this is equal to the average of p squared over phi k minus phi k p phi k squared. Okay? So this is 0, but this is equal to 2m ek. Okay? So as you increase your eigenvalue, the spread of momentum increases. Okay? What about the spread in x? Okay? There is an exercise that asks you to calculate the spread in x for these states. Okay? The square. Okay? Which is essentially phi k, the value of x squared minus the value of x squared. Okay? Try to do this exercise and try to see what happens to the spread in x. You understand that the spread in x will never exceed n. Right? Because it's confined there. And so, since the spread in momentum increases, the Heisenberg bound will be looser and looser. I mean, you are increasing the product of the two as you go further. Okay? So the lowest uncertainty state is obviously the ground state. Try to calculate how much this is close to the Heisenberg limit. All right. The final thing, I'm going slow because this is our first example and it contains some of the ingredients that are somehow useful and to be understood. There is also something that you should appreciate here from this figure is that had I decided to put the origin in the middle, okay, so typically I could put the new origin here and I would say that this point is minus L over 2 and this point is L over 2. Or sometimes you call this A, okay? And this minus A. Okay, in this case I would say that the width of the cell is 2A. There are several things that you can do, just notational convenience. But there is an important aspect in the story in putting the origin in the middle. The potential is more symmetric, okay? You realize that it is in fact even with respect to this origin. Now what about the wave functions? Now look at the wave function that I wrote here as a sine. How does it look with the new
Cos.
origin? It looks like a cos. Okay? Now what about the second wave function that was the sine of 2 pi over L? It looks like a sine. Okay? And if you go on, the next one will be even and will look like a cos, and the next one will be odd and will look like a sine again. So these that in this origin, with this origin were a sequence of sine wave functions, if you move the origin, will be an alternating sequence of cosine, sine, cosine, sine, cosine, sine. Okay? And alternating sequence of even, odd wave functions. Okay? So you can even classify the parity of the eigenfunctions if you select the origin in the middle, and you would just understand that the ground state is even, the first excited state is odd, the second excited state is even again, and so forth. Okay? And the basic algebra behind is essentially the following. If I put this origin here, and I call this y, then y is equal to x minus L over 2. Okay? So if x is equal to 0, this is minus L over 2. If x is equal to L, y is L over 2. And I can rewrite, so if you want, I can write that x is equal to y plus L over 2. Okay? Now I take the state sine of k. Remember that k is n pi over L, x, okay? And I rewrite it as sine of n pi over L, y plus L over 2, okay? Do you follow me? I have simply changed my, sorry, maybe y is an unfortunate label for the abscissa, okay? Do you want to call it x prime? Okay, x prime is perhaps, because maybe it makes you confused. Okay? Okay, let's call it x prime. Okay, in the new, with the new choice of the origin, this is the sine of what? N pi over L x prime plus, let's see, L and L goes, N pi over 2. Okay? So you see that for n equal 1, you are summing a pi over 2 to the sine, which means that you transform it into a cosine. For n equal 2, you are summing a pi, leaves a sine. For n equal 3, you are adding 3 pi over 2 and transforms the sine into a cosine, and so on and so forth. So this additional multiples of pi over 2 makes the sine to change phase into alternating sine and cosine. Is it clear? Okay? So sometimes this choice of origin is useful, especially when the potential is not infinite, but you want to do a finite square well, which we'll do later on. Then putting the origin in the middle is actually useful. Okay? Because we can use symmetry in a more effective way. Okay? So later for this. Questions so far? Now there are a few exercises that I ask you to do. Okay, in particular there is one about exercise 2.4, which I would like to signal because it's related to something that somehow you said about the minus sign. So I ask you the following thing. Suppose that I prepare at time t equals 0 the particle not in the ground state, not in the second excited state, but in a combination of them. Okay? So my psi at x t equals 0 is 1 over square root phi 1 of x plus phi 2 of x. Okay? Why did I put the 1 over square root in front? Normalization. These are individually normalized. If you calculate, you might say, but wait, what about mixed products? Well, they are 0 because they are orthogonal. Okay? Try to verify that this psi 0 here, written like this, is such that psi 0 is 1. Okay? Do it. It's simple, but you will notice that there is no contribution from this. So you get 1 times 1/2 plus 1 times 1/2, and no contribution from the cross products because of orthogonality. Fantastic. Okay? So the function is a bit of this and a bit of this. So we'll do something. I don't even want to draw it. Although, notice that here I can choose. Why don't you try to look what happens if I, here, for instance, I put a minus sign, okay? Or here, whatever, in one of these two. As long as you don't keep changing signs, okay, every step of the exercise. Try. Okay, this is the 0 time eigenfunction. Now, what happens to the eigenfunction at time t? What did we say? We said if I have an expansion of this type in terms of phi n of x, all it happens is that you put a phase factor here, right? To do the time dependence. Is it clear? You remember this? Yeah. We said it yesterday. Okay? Now I have only two contributions. Okay? So there are only two terms, and Cn is 1 over square root of 2. Okay? So I just adapt this to the previous thing, and I would have 1 over square root of 2 phi 1 of x times e to the minus I e1 t over h bar plus phi 2 of x e to the minus I e2 t over h bar. Okay? Is it clear? Good. Let's put this factor here in front. So e to the minus I e1 t over h bar over square root of 2, and then I have phi 1 of x, okay, plus e to the minus I e2 minus e1 t over h bar phi 2 of x. Okay? So for time equal to 0, you get the previous one. But this object oscillates in time. With what frequency does it oscillate? You could view this as e to the minus I omega t. Tell me the omega. The difference between the two eigenvalues divided by h bar. This gap. Okay? So the superposition, this is not a stationary state, it's a superposition of two eigenstates. Okay? It has a dynamics. Okay? And the frequency with which things change is exactly the separation between the two energy eigenvalues. Okay? Yeah. No question? No question. Okay, good. This is exactly the reason why atoms absorb photons exactly, well, close by to the energy separation. Because somehow, when you send a photon, means an electric field which has that energy, there is a resonance phenomenon. Okay? So you take the electron, you make it resonate, and it has a possibility of jumping to the next thing. Okay? So it is quite instructive to actually look at what this wave function does, exactly because it suggests that the spectral gap separations are in fact important when you perturb the system at that frequency. Okay? Well, this is the, so try to do the exercise suggested. Now, this is our first example of a 1D problem where we do the Schrodinger problem, and all states are bound states, an infinite number of them, okay? And the eigenfunctions are perfectly normalizable, okay? Fantastic. This is somehow a simplest case with respect to, say, the harmonic oscillator, okay? Where we will see again bound states, an infinite number of them, all normalizable. A different thing happens because rather than having a spectrum that, as you notice, increases quadratically with n, in the harmonic oscillator will be equidistant, okay? But this is just something that we will comment later on. Okay, clear so far? Okay, so let's move to problems where there are no bound states. Let's see if we can do this today. The problem that I would like to do is the following. I have a potential that is 0 up to here, 0, and then it is equal to some value V0, positive, for instance, from 0 on. Okay? So the potential is a step, like this. Now, obviously, this is an idealization of a potential that does something like this, okay, and smoothly goes to this. But I want to simplify things, and I suppose that this idealization is actually my potential. So there is a step. Don't worry, the derivatives don't do anything strange, they are continuous. The minimum of the potential is 0, so we look only for eigenvalues above. Do you expect that you will be able to trap electrons to create bound states? No, there is nothing here that traps things. Okay? Okay? But in fact, as I told you already, there is a slight difference between this part of the energy and this part. Why? Because in this case, if I send an electron with this energy, it will bounce back. Okay? What happens here? Zero wave function? Not quite. There will be an evanescent wave. Evanescent wave. Okay? So anticipate this, the solution we will get when the energy eigenvalues is in this region is a wave that you send, bounces back, but leaves a little evanescent wave entering into this classically forbidden region. Remember that classically you would just bounce back and not enter the region where the potential is higher than your energy, right? Here, quantum mechanically, you can enter a little bit, okay? We'll see later on. On the contrary, if the energy is bigger than the step, okay, you can in fact go here, but there are two solutions, because you could also come from plus infinity, okay? So here, doubly degenerate solutions, a bit like for the plane waves, okay? You have e to the ik and e to the minus k, all with the same energy eigenvalue, k squared. Here, no degeneracy, okay? Only one state. Okay, where do I start? I think I start, okay. Yes. I start from the second case. From the case where E is greater than V0. Okay? Let's see. So, I want to find, for instance, wave functions in this region. Okay? This is a region where the potential is 0. What would you suggest? Eh? E to the ikx or e to the minus ikx, right? Both of them would have which energy? What do you think? Ek. In other words, the value of the energy I'm looking at, how is it connected with this K? Don't be afraid about this. Suppose that this was the only thing you had. Then you would say plane wave e to the ikx or e to the minus ikx, and the energy would be?
V0 plus.
No, V0 is 0. Okay, so
Well, then just
h bar squared k squared over 2m. Now it could be simpler, okay? Don't look at the complication. The complication will come in a second. I want this region here. Fantastic. Okay, good. What about solutions in this region here? In this half region. Again, don't look at complications, okay? So this, given an energy, what would be the solution here? Not K, not K, some other Q, because after all, so e to the IQx, I want that h bar q square sum to the V0 that I now have makes the energy Ek that I have already chosen, okay? Given an E, which is above this fixes the K in this following way, but the same E should also match with the wave function here, which therefore cannot have K, should have some other Q, right? Such that the kinetic energy plus the potential energy is the total energy. Is this clear to everybody? Okay? Good. And so, okay, Q is equal to, let's see, Ek minus V0 square root of 2m over h bar square. Okay? So this is the value of Q. Where here, obviously, this is related to K, so I could write it in terms of K if you want. Fantastic. Now, what about e to the minus IQ? Okay, the same. So what do I write? I write the following. Let's see. The phi k of x equal to some constant a times e to the ikx plus some constant b e to the minus ikx for x less than 0 and some constant c e to the iqx plus some constant d e to the minus qx for x greater or equal to 0. Do you agree on this? Fantastic. We have 4 unknown functions, 4 unknown constant. What conditions can I impose? Well, the wave function must be continuous, okay? So 1, continuity in x equals 0. The second condition is continuity of phi prime in x equals 0. Okay? We agree on that, right? So 4 unknowns, 2 conditions. So we cannot solve it. It's underdetermined. We cannot find 4 things. What's the point here? How comes I cannot solve it? I mean, I have many solutions.
It's because we might choose that the incident wave is only from the left side.
We'll see that this is in fact a way to handle the difficulty. But in principle, this counting already tells you that there is a double infinity somehow of solutions, right? Now you might say, but one is related to the overall. I mean, you always have a normalization factor in front. So one of this is really not important, as I'm saying. Although you might say, wait, normalization, these are plane waves, so they are not normalizable. Nevertheless, you can rescale and you try to impose some given normalization factor. So one is not important, but the second is a genuine extra possibility. And this is related to the fact that I told you that the solution is doubly degenerate. So if I form one solution, I can also form another one. Okay? So take for a second my way of looking at this problem, which is the following. I write this as e to the I kx plus rk e to the minus I kx. And here, this as tk e to the I qx. Okay? So notice, I have chosen this to be 1 and this to be some function r of k. It's called the reflection coefficient. Okay? This to be the transmission coefficient and this to be 0. I just go with it. Okay? Now let's look. Now I have two unknowns. A reflection and a transmission. And two conditions. So you agree with me that I will be able to solve it. But you might say, yes, but where did you hide, as you were saying, the other solution? Well, the argument is as follows. This is a solution, but certainly phi k star of x is also a solution degenerate with it. Okay? So suppose that I have solved it and I found that this is a solution with energy Ek. What about phi star? Well, remember, this is minus h bar squared, the second derivative of phi k over 2m divided with respect to x squared plus v of x equal to ek, equal to ek phi k. You see, everything is real here. So take the star. Phi star is absolutely a possible solution. But if you look at phi star is different, right? Phi star, okay, now I write in thing. So I have a minus here, a star here, a plus here, a star here, and a minus here. Okay? So you see, we might say, okay, but these are roughly the same. Both are present. Here, the wave is coming somehow from the right, okay? And this is reflected again with an R star. But here, somehow this is only the transmitted, sorry, this is only the wave which is going, sorry, no, I'm messing up. Okay, let's.
And if you have the conjugate of phi k, also the domains of x will also change.
No, the domains are the same. The domains are the same. But what I did here is something a bit too fast. Okay. So phi star is also a solution. Okay. Now let us use the fact that phi k is a solution and phi k star is also a solution. I can make a combination of them. Okay? And now you see that I can, if I combine the two of them, what I have in general is this term, this term, this term, and this term, right? So just let me write it as a I to the kx plus b e to the minus kx, c e to the I qx plus d e to the minus I qx. So I somehow have reconstructed the four numbers that at the beginning I started with. Okay? But now I have a simpler job because somehow I have solved my problem for phi k. I know that there is another solution. I can find whatever combination and I have still solved my problem. Okay? So somehow I have cut the problem in a simpler one where I can actually study this problem in a simple way. Okay? Is it clear? So in some sense, I can also view this problem as, for instance, a problem where you have this wave to the right, so something that impinges into the step is reflected back and then is transmitted here. So I can also exchange the role of what I call the incoming wave, and I let it income from positive x rather than from negative x. I can also do that, okay? So I can define reflection coefficient and transmission coefficient for the opposite problem. They are all inside this possible way of doing the problem, okay? So if you allow me, I will postpone those complications. There is a problem that asks you to think about this problem in more detail, but now we just concentrate on this way of writing the wave function, and therefore I have two quantities which I would like to determine. Okay, how do I determine? Okay. Well, let's write. So I erase this part. There's not much time, but I think we can solve it. Okay. So at x equals 0, the function on the left, okay, is this. Okay. So when you put k equals 0, x equals 0 is 1 plus rk times 1. Okay. Is it clear? This is the function that you have here if you put x equal to 0. This should be equal to the function that you have here when you put x equal to 0, which is dk. Okay? So this is the continuity requirement. Clear? Now take the derivative. The derivative of this object is ik e to the ikx, and the derivative of this is minus ik rk e to the minus ikx. Is it clear? And the derivative of this is iq tk e to the iqx. Okay? Now, the derivative, when you put x equal to 0, is ik 1 minus rk. Is it clear? I put this thing and I put x equal to 0. I put ik as a common factor, there it is. The derivative here is this. You put x equal to 0, you drop this, it's iq times tk. Okay? So the I, in fact, disappears. And I have essentially the following two equations. So I rewrite them here. Tk is equal to 1 plus rk, and then I have q tk, which is equal to k times 1 minus rk. Okay? Did you follow? The algebra is simple, you can redo it. But this is the position of these two conditions. Now, I substitute, this is a linear system for these two unknown, rk and tk. Very simple. Substitute, for instance. Okay? So this would be q times 1 plus rk, okay, equal to k times 1 minus rk. Okay? Which means that if you solve for rk, you will find that rk is equal to k minus q divided by k plus q. Believe me, just bring, for instance, the rk on this side and this q on that side, and you see I have k minus q, and on this side I have k plus q. Okay? So when you do the algebra, is it comfortable for you or it was too fast? Okay, good. So rk is this. What about tk? Well, tk is 1 plus this. Okay, so tk, I can write it as, well, 1 plus this is k plus q divided by k plus q. This is the 1 plus k minus q. Okay, so the q in fact goes, and tk you can also write as 2k divided by k plus q. Okay, that's the solution. You fix whatever energy you want. I determine a k. From this I determine a q. Okay, so the k, the k, the q, and that's it. I have the r and I have the t. Reflection and transmission. Okay? And this fully solves for my wave function somehow scattering from minus infinity. The star would be still allowed, and I can superimpose with whatever coefficient this two degenerate solution. Okay? Is it clear? Now, we don't have much time, but let me discuss a few things. We will finish the discussion tomorrow. But suppose that I want to do now the second case, which is looking for an energy below the step. Okay? I expect that here there is no degeneracy. How would you write the solution to the left? Well, the same way, right? What about the solution here? So don't look at the complication. I have an energy which is below the minimum of the potential. Isn't this forbidden? Huh? Why?
Your Q will be imaginary number.
Yeah, this is the solution, but I'm asking, why is that? That now I ask you to consider an energy that is below the minimum of the potential in this part. Isn't this something that I told you not to do explicitly?
That is not the minimum of potential.
It is not the minimum, first of all. The minimum is this. But if you look at only this part, it is similar, sorry, maybe I should erase here. It is similar to the following problem. Suppose that I tell you the potential is 0. Okay? And I ask you to find plane wave solutions, or, I mean, exponential solution with an energy that is negative. Can I find it?
Yes, but the momentum for that will be complex. That is 1.
It would be e to the qx or e to the minus qx. These are both wave functions such that if I take, let's see, this is minus h bar squared, the second derivative of this function, for instance, of e to the qx. How much it is?
Minus q squared
Equal to minus h bar squared q squared over 2m times e to the qx. Okay, so you might say, here I have my nice negative energy eigenvalue. But this wave function, e to the qx, is not good.
It's not
Why?
Normalization.
Because it does something like this.
Exponentially.
Okay? So over the whole space it in fact diverges, and it's not only not normalizable, this is something that we can, with some plane waves are also not normal. But it's physically very strange. It tells you that the probability of finding the particle at plus infinity increases without bounds, I mean, in a dramatic way. So this is certainly not good. But if I ask you, forget about positive, look out only at the negative ones, then this is a reasonable thing to do, okay? So if you look at only half space, and you forget about the other half, this is a good solution. And the same happens for the other one, for this, okay? It would be a function that if you plot it over the whole space, is like this, okay? So obviously very bad at negative infinity. But if I don't look at this region, it is a perfectly reasonable wave function. In fact, the evanescent wave that I was discussing before, okay? So, solution to the problem is that to the right, now, I shouldn't write the solution in this way, but I rather should write it in the following way. let me just follow the notation, tk times e to the minus qx. Okay, so to the left as before, e to the ikx plus rk e to the minus ikx, but to the right I write it like this, without I here. Okay? And obviously now Q is such that H bar Q is equal to, here H bar Q was this, you see, positive. Here H bar 2 is almost the same, but now it's V0 minus Vk. Okay, it's opposite. And this is now, in the second case, a positive number because Ek is below that. Okay? So you can verify that indeed this evanescent wave only in half space is perfectly allowed with this wave vector Q. Now you might say, okay, do I need to redo the algebra? Well, in fact, not. If you take the Q I had here, okay, and you change it into IQ, you see that this e to the IQx changes into e to the minus qx. Is it clear? Take this object and substitute q with IQ. I get the minus that I have here. Okay? So either you redo the algebra or you believe me, and the RK are k minus IQ divided by k plus IQ, and TK equal to 2k divided by k minus IQ. Okay? No, sorry. Take plus IQ. This is the solution of the new problem. Okay? I obtain it with this trick, or if you don't believe, just do the algebra as we did on the first case and you will find this solution. One thing that you should observe, however, is now that this is a complex number divided by this complex conjugate. Okay? So somehow Rk now modulo square is 1. Okay? And we'll comment on Tuesday, finishing this exercise, on why is it that somehow you are obtaining a reflection coefficient whose amplitude is exactly 1. Because you can prove that essentially there is no current, if I calculate it, remember the current density, there is no current in this region, okay? And there should be also no current here. So the e to the ikx brings a current, and the e to the minus kx should bring an equal and opposite current to have J equal to 0 everywhere. Okay? So next time we'll do considerations about the current density, and we will discover why we need Rk equal to 1 in modulus in order to have 0 current everywhere. Okay, so more about this next time, where we will do also the finite square well. So this will be probably the last problem we will do. So the square well like this, which typically is put symmetrically around the origin, and typically you call 0 this, and you call minus V0 the depth of the well. We'll try to solve this finite square well problem because it's an interesting exercise. Okay, good. See you on Thursday. Yeah.
When are we going to receive the second chapter?
Today.